Let's concentrate then on the annual maxima method. So, annual maxima, first of all, what is the premise? The premise is that we get one observation per each year, which is an high flow, it's supposed to be an high flow, and we want to estimate its frequency of occurrence. Our target should be to estimate a probability distribution, so an analytical representation of probabilities for high flows. And we need an analytical representation in this case precisely because we want to extrapolate. Because, for instance, when we look at the Po River, our time series is extended for 90 years, but we may be interested in estimating at what frequency very high flows, even higher than the ones that we observed during this 90-year period, may occur. And therefore we need to extrapolate. So we are not just interested in the frequency of the values that we observed of flows, but we want to extrapolate. So we need an analytical representation. Keep in mind, as a second premise, that usually when we talk in technical terms, the laws and our clients don't ask us the estimation of a river flow, high flow for a given probability. They speak not in terms of probability usually, they speak in terms of a return period. So the first, one of the premises that I want to make is that there is a correspondence when we deal with the annual maxima method between probability and return period. And in particular between probability of not exceedance, which is what we are interested in, and return period. Okay, so first, when I talk about probability of not exceedance, which I may call with the symbol, let me see, kind of symbol fx, yeah. But let me see, just one second, I have a doubt about the consistency of these symbols, because I call with I think, just one second. You know, I'm thinking because in the textbooks, sometimes you see probabilities called with the symbol capital P and sometimes with capital F. And when they use these symbols, probability density is often called lowercase p or lowercase f. The problem is that here, I noticed that I have been a little bit inconsistent because I called frequency with capital F, which is usually done in the Italian literature. In the Italian literature, frequency is called with the symbol capital F. And then I use again capital F to mean cumulative probability. And therefore, I think it is because I used the lowercase f for probability density, and then here I'm using again capital F as cumulative probability, probability of not exceedance. So which is something that I need to change. So I will make a change here, and I think that the best thing is that if I keep f for frequency and I use for probability, but oh, let me see. Okay, I will see. Okay, what I need to change, because I would like to keep lowercase f for probability density because it's the most widely used. So I need to keep it. I need to keep capital F for probability of not exceedance, which is the integral of probability density, but then I need to change the symbol for frequency that I used above. And probably I will use FR for frequency. So just be patient on that. I noticed that, and I will change the symbol for frequency. Okay. Okay. So let's then use lowercase f for probability density and for probability of not exceedance, capital F. Okay. So as I said, there is a one-to-one correspondence between the probability of not exceedance within the method of annual maxima and what is called the return period. What is the return period? By intuition, you can understand what it means, but let's define it. So the return period, and I define and I write. While I define, I'm writing. So the return period is the average time interval between two events reaching or exceeding a given threshold. So let's look at it. The return period is the average time interval between two events reaching or exceeding a given threshold. So we fix a threshold for river flow, and then we look at the events that reach or exceed that threshold, and we look at the time distance between them. And we compute the average time. Don't forget to say average. You can't say that it's the time between two events. Because if you forget average, it means that you are meaning that the time is precise, which of course it's not true. I mean, if I have a flood today, I cannot exclude that I have a flood tomorrow, even if the last one was 200 years ago. When we speak about probabilities, we must always speak in terms of statistics. Okay. The wording may be a little bit different here, but the meaning is the same, because I went by memory here. So, now, you understand that the return period is related to frequency, of course, and probability is related to frequency. So there must be a correspondence between probability and return period. And indeed, it exists. Let's suppose that we indicate the probability of an event has capital Fx, probability of not exceedance, because we are talking here about reaching or exceeding the threshold, which is the same thing that saying that we don't exceed the threshold. I mean, they are complementary. So when we speak about probability of not exceedance is complementary to the probability of exceeding. Remember that probability over the whole domain of existence of the given event is 1. Cumulative probability is 1. We already proved it. And therefore, if we fix a threshold and we get the probability of not exceedance, the probability of exceedance is 1 minus the probability of not exceedance. Okay? So, of course, there must be a correspondence between the probability of not exceedance and the return period. And in particular, if we indicate the probability of not exceedance with Fx, then, and the return period is indicated with Dx, if we compute this ratio, Dx minus 1 divided Tx, we get the probability of not exceedance. And you may say, can you say something more to make it clearer? Okay, fine. Let's suppose that you have 10 years, and you want a return period of 10 years, and you want to compute the corresponding probability. And so Fx is equal to, in this case, if the retro period is 10 years, it's equal to 9 divided by 10 is equal to 0.9. Is this reasonable? Yes. Why is that? Because let's suppose that you have 10 years of data. And what is the retro period, more or less, of the highest value in 10 years? The retro period is 10 years, okay? So you get 10 maximum, 10 annual maxima. What is the retro period of the highest value? It occurred once in 10 years, so you expect that more or less the retro period is 10 years. And what is the probability of not exceedance? The probability of not exceedance, in order to compute it, you have to compute the number of times that the highest value was not exceeded and divide by the number of data. The number of data is 10 because it's 10 years. The number of times that was not exceeded is 9. And so you get that the probability is 0.9. So we proved very simply that the retro period of the highest value in 10 years is 10 years because it occurred just once. And the probability of not exceedance it's 0.9. Look, indeed we are talking here not of probability but of frequency. FR, okay? So I said probability, but I should speak about frequency because I'm referring to just 10 years. It's not a long period. And I said that the retro period is 10 years, which is not really true because the retro period I should look at the average. And if I have only 10 years, I'm not making any average. I'm taking the highest value and I say, okay, this occurred once in 10 years. I'm not computing any average. In the next 10 years, the same value may occur 5 times. Okay? But even if I am making a reasoning on frequency and approximate retro period, because I'm not talking about average, but just of one experiment, still it's clear that the probability is related to the retro period in this way. And keep in mind this relationship, which only applies, be careful, for the annual maximum method. Because in the annual maximum, I have one event per year. So I can say this. I can write in this way. If you take a peak over threshold, in 10 years you may have 30 events. And therefore, the frequency doesn't correspond anymore to the length of the period. Because the highest value would be 1 over 30 if you have 30 events, but the retro period would be, anyway, 10 years, because the length of the period is the same. So this reasoning here only applies if you refer to one value per year. But still, this is extremely important. So keep it in mind, because usually when you make a design project, the laws tells you if you are designing for a bridge, you have to design against a retro period of 200 years. If you design for a dam, you have to design against a retro period of 500 years. If you design for a sewer system, you have to design for a retro period of 5 years. And this is what the laws tell you. And of course, you must translate into probabilities if you want to make design. Okay, so this is the premise that is essential. A second premise. When we apply probability to historical data to make inference for the future, we are implicitly assuming that the past is representative of the future, which is a question today because people say that there is climate change, people say that there is land use change, and this is true indeed. And therefore they say the data may be not representative of the future. If we assume that data are representative for the future, we are assuming stationarity of the underlying process. Stationarity refers to the model that we apply to make our design project. So basically what do? We estimate a probability distribution of past data and we use the same probability distribution to make inference for the future at a different time. So we assume that our probability distribution doesn't change in time. This is the definition of stationarity. And you may look at the link in Wikipedia if you want to know more. This is highly debated today. Highly debated because, as I said, there is a convincement that stationarity is a weak assumption today. Still, it is a working assumption, and keep it in mind. It's a working assumption. It's not an assumption on what occurs in the real world. We are aware that something is changing out there, but in order to be able to make inference, in order to be able to get a value for a project, we are assuming stationarity. And what I suggest to students is that this assumption, as any other assumption, needs to be critically evaluated. So you need to make assumptions if you want to design. It's needed. So this assumption is, like any other assumption, may be reasonable, maybe not. So look at your process, look at the status of the river. Did the river change a lot in the past? You look at the Po River. Is the status of the Po River changed a lot with respect to the past 90 years? I would say no, it's not changed. No new dams, no new training along the river. There is climate change, but climate change didn't affect much the river flows, because if you see at the past, you see that more or less the regime of droughts and floods is not changed. So in my opinion, stationarity is a reasonable working assumption for the Po River, but for other rivers, maybe not. Like for the Danube, people tell me that the Danube was trained a lot of barrages, a lot of changes, and therefore the assumption of stationarity may be not reasonable. Like any other assumption, I say again, you should evaluate it and make your consideration. I'm spending a little bit of time on this because stationarity, if you look at even at newspapers, you see people saying that the real world is not stationary, and this is not correct, because stationarity is a working assumption. It's an assumption of the model, not on the real world. And I think that stationarity may still be a reasonable working assumption even under climate change and land use change. It depends. It's a working assumption. It's not an assumption on the real world. The real world is, of course, it's neither stationary or non-stationary. The real world is continuously changing, and it's not probabilistic. We treat the real world with a probabilistic model because it's a convenient way to treat it probabilistically. But the real world is not probabilistic. It has its own trajectory, which is just one, and it's that. Okay, so stationarity and I think it's fine. Now, let's define a probability distribution to describe the extremes. There are several distributions called extreme value distributions that you may use. The most used one is, because it's very simple indeed, it's the Gamble distribution. It's widely used, even if there are distributions that are today preferred. Gamble distribution. First of all, Gamble was a German scientist, German statistician, and people told me that the pronunciation wouldn't be Gamble, but would be Gumbel, like we say in Italian. In Italian we say distribuzione di Gumbel. And in the English literature, English-speaking world, it's called Gamble, but probably the correct pronunciation, as I said, is Gumbel. Okay, but anyway, this is not important for us, just in order to be understood. And it's the Gamble distribution, like any other distribution, is an analytic function giving the value of fx. I want to use the same symbols, and therefore it's written in this way: e to the power of minus e to the power of minus x minus me divided by beta. Let me see if the symbols are the same. Yeah. Okay, and it's a double exponential. Don't be concerned by you know, this structure, it looks complicated. It's not. And I will show you that it's absolutely not complicated. And you have to learn it by memory. Sorry for that, not the Gaussian distribution. The Gaussian distribution, I don't require students learning it by memory. For the gamble, I please, for the exam, make an effort to learn it by memory. It's extremely important. And as an engineer, you need to know some very important relationships by memory, like the Chesy relationship, the Chesy formula for open channel flow, for uniform flow. And this is a formula that I tell students you cannot get a degree in civil engineering or hydraulic engineering without, or environmental engineering, and claim that you are an expert of river flow and you don't know, you don't remember the Chesy formula. And there are some formulas that one needs really to know. So, for instance, the second law, Newton law, F equal m times a, that you need to know it by memory, and I would also include the gamma distribution. If you are an engineer, there are some relationships that we must know. And Chesy relationship, and also I suggest you, if you are dealing with rivers, with water resources, you must know how to compute the uniform, the depth of uniform flow, which is Chesy formula, and also how to compute the depth of critical flow. These are things that you need to know. Okay, so this is the gamma distribution, and there are two parameters, because you see here x, and two parameters, mu and beta. You don't see time here. It just depends on the parameters and x. The fact that you don't see time means that it's stationary. Okay, and now the question is how to compute mu and beta. And mu is equal to, let me use the same symbol, it's m here. Yeah. So basically, you can write it in this way. Okay, let's refer to the slides. I don't want to make confusion because I was writing in a different way. Let's refer to here. So me, it's let's start from. In order to make it very clear, because me is the mode and the median is okay, but I'm not interested in this one. You don't need to remember this. We need to remember this one. And go down. So let's start from this one. This is the average of x, so you can compute, given your sample of annual maxima, you can compute E of x like the average. And therefore, once that you know the average, here you have a relationship that relates the average to mu and beta through lambda, gamma. Gamma is given by this value here. So you have a first relationship where you have still two unknowns, which are mu and beta. Ex again is the average of your sample, and gamma is 0.5772. And then you have to look at here, this relationship here, which says that the standard deviation of the distribution is equal to this value. So let me write on the blackboard now. Sigma is, let's indicate it with the standard deviation, which is given by beta pi divided by square root of 6. So, what is the standard deviation? The standard deviation, I think you already know what is that, but it's the statistics of the data. And basically, you know how to compute, let's suppose that we have a sample xt, or Qt of annual maxima. The average is, of course, given by the summation of Qt, and the sample is n data. N is the number of observations that we have. And the average value, of course, is the summation of Qt divided by n. And the standard deviation, sigma, of Q is equal to 1 divided n minus 1, which multiplies the sum of Qt minus EQ square, and then there is a square root here. So, first of all, I take the difference between each observation and the overall mean, I square it, and I sum it over all the observations. I divide by n minus 1, and I obtain the standard deviation by taking the square root. This can be easily found on Wikipedia, how to compute the standard deviation. So, once that the standard deviation is known and you compute it from the data, so it's very, and there is a function in RSD, standard deviation, SD of the vector, you get it. Of course, through this relationship you can compute beta, because it's the only unknown. Beta only depends on the standard deviation. And then you go up there, you look at the relationship for the mean, you know beta at this stage, and can compute mean. So with a very simple couple of relationships, you can compute mean and beta. You only need to extract the annual maxima, compute their mean, their standard deviation, and then you compute beta from there and mean from here. Very simple. Okay, now we have everything known here. So the next question is, perfect, I estimated mean and beta, how can I compute the river flow for a given retro period? Very easy, I show you. So I'm deleting what is related to estimating the parameters, mean and beta, because we already archived it. And please try to repeat what I'm doing now, because it's simple, but you need to be able to do it. Also for the exam, it's important. My purpose now is to fix f and compute the corresponding x. First, let me say that fx is equal to tx minus 1 divided by tx. I want to speak in terms of return period. So I can substitute here and write that tx minus 1 divided by tx is equal to e to the power of minus e to the power of minus x and me divided by beta. So what I want here is to go inside here with t and to get x. And thanks to the easy structure of the gamma distribution, we can compute it explicitly. We just need to take two logarithms, because we need to eliminate these two exponentials. So let me take the first logarithm. The first logarithm is logarithm of, and the logarithm is with base e, of course. tx minus 1 divided by tx, and this is equal to minus e to the power of minus x minus b divided by beta. Of course, by taking the logarithm, I can eliminate one exponential at the right-hand side. And in order to move forward, let me change sign. So let me change sign directly on the blackboard in order to speed our calculation. Okay, now I need to take the second logarithm. So I have logarithm of minus logarithm of dx minus 1 divided by dx. This is equal to minus x minus me divided by data. This is not reported here. Be patient. This is something that I didn't write here. But still, you have to know this, how to do this, because it's just taking two logarithms. You know, it's something that I didn't report there because I thought that it's quite trivial. Let me change sign again, and then we are almost there. We can write, if I multiply both sides by beta, I obtain, and I invert the sides, x minus me is equal to minus beta logarithm of minus logarithm dx minus 1 divided by dx. And now we are there because we only need to bring me to the right hand side. Okay? So let me write here plus me and remove it from here. Let me write it again here because I want just to show you that there are several different ways of writing this final relationship. First of all, remember that in some textbooks, instead of using beta as parameter, they use its reciprocal. So you may find beta at the denominator here. It doesn't change anything, it's just a matter of convention. Second, people usually don't like to have negative signs, especially engineers. They don't like negative signs because I'm not sure if you noticed that. If you speak with physicists or climate scientists, they don't matter. They are not concerned by complex numbers, negative signs. They treat complex numbers as real numbers. If you speak with engineers, usually they are very much scared by complex numbers, and also negative signs is something that engineers don't like because we are used to deal with positive quantities. And therefore engineers usually try to rewrite this equation by avoiding negative signs, and therefore they write something like that. X is equal to me minus, because negative sign is not a problem for an engineer if it is after a positive quantity. But if it is at the beginning, it's a little bit concerning. So they write me minus, and then write logarithm, and then in order to avoid the negative sign in front of the second logarithm, one could say that it's, one could invert numerator and denominator. So you may find it written in this way. Doesn't matter. Look, there is something that is missing here. Let me see, because I don't see beta. Sorry, it's here, minus beta. Sorry. Okay. Look, this relationship, it's extremely simple. Once that you have the return period given by laws, you only need to know mi and beta to compute the peak flow. And mi and beta can be computed through simple statistics, mean, standard deviation, average, and standard deviation of the annual maximum. So it is indeed extremely simple. If you make this computation in Excel, it takes less than 2 minutes. If you give me the series of the Po River already with the annual maxima, it takes me less than 2 minutes to compute the peak flow. Because I compute average, standard deviation, and then mi and beta, and then I go inside this relationship. It's very easy. What are the drawbacks? What are the things that you need to pay attention to? First, we used an analytical relationship, which is the gamma distribution, to express probabilities. And we are not sure, we didn't check that this analytic relationship provides a good, a reliable estimate of probabilities. So we need what in statistics is called goodness of fit checking. We need to attest for the goodness of the fit of the gamma distribution to our Po River, whatever, annual maxima. And the literature provides plenty of tests to prove it. And here you see, here there is an example of application, very simple. Look at it because it clarifies, and you see that it's very simple to compute the peak flow. But then there is a section titled, is the gamma distribution fitting the data well? Please read it. We are not dedicating time to it because we don't have time. And also, it's not really very central statistical testing to what we want to do, but keep in mind that it's needed. It's trivial, because statistical testing is nothing complicated, but of course one